Hello everybody, so today we're going to talk about how to use the trapezoidal rule when given a function. So an example of a function might be given could be f of x is equal to x squared plus 2x plus 5. Now it might seem weird to think that we can use this with the trapezoidal rule, but in fact we can, because when you think about this function, it's probably going to look like a curve. If we were to plot it, we would have some kind of a curved shape like this, or depending on the shape, like this. So we could use this to plot the area underneath that curve. So we'll go back to the function we're looking at for now. We probably need to look at it in a specific domain. So we could say that x is between 4 and 0. Now, just like when we're given a function normally, we want to know what the different points along the function are. So we're going to find all the different values between 0 and 4. We're going to sub them into our function. So we're going to get f of 0, f of 1, f of 2, f of 3, and f of 4. If we get f of 0, that will be 0 squared plus 2 times 0 plus 5, which will give us 5 overall. If we get f of 1, that will be 1 squared plus 2 times 1 plus 5, giving us 8 overall. And the rest we can fill out and sub in similarly. Now, we don't actually need to plot this onto a graph, but just so you can see where it ties into the trapezoidal rule, and we're just going to do that for this specific example. So what we'd see is we'd have an x-axis and a y-axis. At 0 on the x-axis, the y value will be 5. At 1 on the x-axis, the y value will be 8. At 2, it will be 13. At 3, it will be 20. And at 4, it will be 29. So if we were to plot that curve, it would look something like this, part of a quadratic curve. What's special about this though is that we know for each of these what the individual heights is. We know this is 8, we know that this is 5, we know that this is going to be 13, that the next one is going to be 20, that the final one is going to be 29. So this will really be a calculation now at this point, very similar to our trapezoidal rule calculations. The only difference is that the beginning and end of the domain and range, so the first and last term that we come up with, are going to be our first border of the shape, the last border of the shape, and all the in-between ones will fit into the formula in between themselves. So let's write out the formula now. So we have a formula here. The area is approximately equal to the distance in between them, which in this case is going to be 1 because it's going up by 1 each time, times the first height, which is 5, plus the last height, which is 29, plus 2 times all the different heights in between. Filling in what we know now, we could say the area is approximately equal to the gap, which we said is 1 because it goes up by 1 each time. 0 to 1 is 1, 1 to 2 is a difference of 1, 2 to 3 goes up by 1. So it'll be 1 over 2 times the first height, which is 5, plus the last height, which is 29, plus 2 times all of the heights in between. So that'll be 8 plus 13 plus 20. We use BIMDIS now to try and solve this out because we have quite a lot of different components. So we always start with the brackets, and we start with the brackets that are the most inside. So it's going to be 8 plus 13 plus 20. This will give us 41. Two times 41 will give us 82. And then when we add this all bracket here together, we get 116. Now a half times 116 is going to be 58. So you can say the area underneath that curve or underneath that function is approximately equal to 58. Now we're not told if it's centimeters or meters, so we can just say units squared here.